Usually when you do optimal control, you start with a finite horizon, standard optimal control, and then infinite horizon, and then you look at optimal stopping, and then at last you get to the target problem, right, from an academic point of view. But this was not my motivation. So my motivation came from, so I will just mention what the stochastic target problem is. So usually, basically what we do is to ask of the minimal amount or the minimal amount of x that we need so that we can transport an object through a diffusion process so that it reaches a target. So this is a very highly academic terminology. These are two concrete problems that I was faced with, and these are the reason why I was interested in this problem. So the first one was asked by two companies, one in Algeria and one in Saudi Arabia. So the idea is like this. They want to frack oil or gas from shale, right? And they need huge amount of water. Of course, water in the desert is very expensive, and it has a social effect and so forth. So the question here is, what is the minimal amount of water you need to extract gas or oil, given some control? So what is the control here? These are exactly, so the pipe dimension, the pressure, the environment, the transportation, and all that stuff, right? This is a very tough problem for me. I don't know how to solve it right now, right? So the second problem, so I looked around, target problem. You go to France, you meet Nizar, you go to ETH, you meet Meta, and they tell you they know everything about it, right? So okay, so they send me to two guys, Idris and Bruno Bouchard. These are big specialists in this field. So I talked to them, and they produced, so everything nasty here is their fault, right? Okay, so the motivation in this big project comes from the so-called super application problem. Super application problem is like this: find the minimal amount of money you want to invest at time zero so that you get some amount at capital T, right? So, and I have another application that came from crowd dynamics, or we would like to design strategies for optimal evacuation in case of accidents or like in everyday life here. So, and the application was in connection with the project I did together with Hamidou Tambin regarding the Dubai Tower. So the question that they were interested in is the following: how many people, how many persons should we have? What is the optimal number of persons should we have in the building so that we can perform an optimal evacuation in case of emergency? And this is also a big question that I don't have any answer to. So what I do, basically, I just follow the traditional. So an aspect here that has been discovered by Sona and Tuzi and their co-authors is that if we consider, let's see. So if we consider this problem, so usually pathwise constraints are costly, so that you cannot afford them. So what you do, you want to relax these things, and the technology here is two-step technology. The first step is to establish a geometric dynamic programming principle, and the second step is to try to derive a Hamilton-Jacobi-Bellman equation related to it. So these are basically the main steps here. So, and everything relies on the fact that we have the flow property, right? So let's see, it doesn't work. So we have this flow property, which means that you can start afresh from another point in the future without altering the dynamics, right? And from this, they could derive dynamic programming principle, and so the the indicator function of the complement of the reachability set solves an AGB equation. And of course, they did a lot of work here. So because they observed that the cost is too high, so they wanted to relax it. So relaxation means that you don't look for almost true constraint, but you look for a kind of expected value of some functional, right? And of course, if we can solve this problem, then we can solve the almost true constraint. Just put p equals 1 here, and we get it. So the technology for it is, so this has been discussed even by Fulmer and Leukert in 1999 using the Neyman-Pearson's lemma, but Bouchard and Elie, who is here, solve this using the Martingale representation theorem. So what we do here, because my co-workers come from the same family, so we try to apply the same technology here. Okay, so this is the idea. So because we are in mean field conference, I should consider diffusion of mean field type or kind of mean field nonlinear control diffusion as the dynamics of my process. So the question is whether this is a natural one that also appears in my previous examples, fracking gas or oil, or in this crowd dynamics. Indeed, it does, because in connection with fracking, we just make the crude approximation. We take just the fluid, the equation of the fluid, or the and make it. So this is an equation for density. So I just make it of mean field type. So this is the idea here. And in the crowd dynamic situation, because the drift and so even if we assume that the volatility is constant or the diffusion coefficient is constant, the drift usually measures the amount of people surrounding the individual. So there is a kind of measure of crowdness or measure of congestion involved in this. So that means it is quite natural to consider this mean field, the dependence of the diffusion on the law of the process at time t. And of course, we would like to consider this time consistent target, because we would like to exploit this dynamic programming principle so that we can solve the problem. By the way, I don't know of any other technique than the dynamic the DPP that can solve this kind of problems. So this is the first open problem here. So the idea here is to try to mimic the classical approach. So the first problem we are facing is that my diffusion process does not have the flow property. So if we start with X, deterministic initial value, so we don't have the flow property. But if we use the initial value as a random variable in a nice space, then the flow property holds. Of course, when you do this, you immediately have an infinite dimensional problem, and so on. So we would like to avoid it, but we avoided it, but it caught us at the end, as we will see here. So okay, so the idea here is just to try to find a way to apply to describe a dynamic programming principle here. So what we said here is just we just describe the expected value using the Martingale representation theorem as where we just disintegrate the probability with respect to the underlying Brouwer motion, and we get a Martingale representation theorem in this way. Using this decomposition, so the constraint becomes a constraint on the what we call the quenched law or the conditional law of the process given the Brouwer motion, right? So using these calculations, we can interpret this constraints in terms of the constraints on the conditional law. Of course, when we deal with these things, immediately come technical problems. Does this conditional law exist? Is it irregular enough to derive the dynamic programming principle and so forth? And these are the details that take much time. So this leads us to consider this type of diffusion processes. If we disintegrate P with respect to this marginal law, the conditional law, we end up with diffusion process that depends on the underlying noise. So we call it a quenched SDE because so this is diffusion process where the coefficients are given are expressed in terms of the conditional law given the environment. So some people call it a common noise issue or master equation and so forth. But this has been known for decades, so people in physics are always ahead of us by at least 20, 50 years, right? So they call it quenched behavior. And if we integrate against the underlying law, we call it a annealed behavior, right? So the interpretation of the target problem now becomes much clearer. So it is a transport problem. So we want to transport the initial law, so the initial configuration of the particles, transport it along this diffusion process so that at time t, the conditional law reached some target. So the target here is G here, right? And G is some set in the space of measures, right? So the idea now is that to write down, to express the reachability set as the set of initial measures mu, such that we can find a random variable whose conditional law is equal to mu, and the final state of the process, the law of the final state process, reaches G almost surely for some control mu. Here comes the probabilistic setup. So this is very important, not only due to technical reasons, which is legitimate, but also I have an idea of trying to make simulations out of it, because at the end of the day, you cannot sell a martingale problem to Samsung that manages the Dubai Tower. So they want figures, right? So this is the idea, right? So the setup is very important because we will need to prove the dynamic programming. That means we need to create some kind of flow property. And because we need a Hamilton-Jacobi-Bellman equation, then we have to put it on the set of measures, which means that we need to to use the sophisticated techniques of lifting that was discussed by Lyons and so forth. And there we need to be very careful, because not all the underlying spaces allow for this lifting. So the underlying space should be rich enough. So this is the underlying idea behind this probabilistic setup. So we consider the probability space as a product of two spaces. The first one carries the Brougham motion, and the second one carries the Lebesgue measure on 0, 1. And the idea behind using this Lebesgue measure on 0, 1 is due to the fact that we will use lifting afterwards. So this is our probability space. We make the product and so forth, and omega is always has always two components, and a component that carries out the Brougham motion, and the second component is carried out by Lebesgue measure on 0, 1. So this technical aspects has the following advantages. To prove the geometric dynamic programming principle here, we need, so this is the advantage. So any predictable or any progressively measurable process to F can be written as a Borel function of omega 1 and omega 2, omega 0 and omega 1. So this is a kind of, what you do, you just make all the processes in feedback form with respect to the underlying components. This is the idea. And this is very useful from simulation point of view. So what you do here, you just try to figure out what is the appropriate Borel measure, the Borel function that you need. Because you can simulate from the Lebesgue measure 0, 1, right? And you can simulate from the Brouwer motion, right? And this is exactly at the heart of what is called deep learning now, right? So you want to find a function that fits a random variable, right? If you cannot find u here, you probably would like to look for some approximation, right? Okay. The second one is less trivial. This is Yankov von Neumann's measurable selection theorem. So this is the main tool that is used in this type of literature in order to derive the Hamilton-Jacobi-Bellman equation. So I just throw it here. Don't look at it carefully unless you want to sleep. But I just mention it because I will not mention it afterwards. So these are exactly the two ingredients. So there is an advantage here of this selection theorem. This is exactly of the same character, but at the measure level. So you can also use it in order to devise approximation schemes. All right. So the Wasserstein space, as usual, because we are dealing with probability measures, you know it. And so this is our controlled quenched diffusion. So we have a diffusion. We start with an initial random variable, and you condition on the probability on the filtration of the history of the Brouwer motion and the underlying 0, 1 random variable. We do it like this, and of course, so this kind of equations should be stable enough, regular enough, so that we can perform this dynamic programming principle. So the results are like this. So assuming some basic assumptions on the coefficients, we can prove existence and uniqueness and stability. And what is important here is that not only we get L2 estimate here, but we also get the flow property, which is the key issue here. So the flow property means that we really can transport things along this diffusion process. The second one is very useful because it comes in the matching argument if you want to make some simulation, because we may discretize this. We may consider discretize the diffusion process, and we know that if we discretize it, it converges properly to the underlying diffusion. Right. So what is the stochastic target problem? The first formulation says that we would like to find a probability measure mu such that we can find an underlying random variable whose conditional law with respect to Brouwer motion equals mu, and the final target belongs to G for some control. The problem here is that we have to find a pair psi and u that satisfy this constraint. And of course, if we are interested in the initial distribution, which is the most important issue here, so this reachability set does not have to depend on xi. So we should choose in xi. What matters here is mu, not xi here. And of course, it is a big problem. It is not easy. I mean, it is not always true that you can find a random variable xi such that the conditional law of xi with respect to Brouwer motion is equal to mu. So this matching problem is not at all general. You need a lot of structure, right? So what we do here, we solve a general. So we come up with a strong formulation, but this strong formulation is made possible thanks to our choice of the underlying structure. So that means omega is just omega 0, which is carried out by Brouwer motion, and omega 1 is carried out by the Lebesgue measure, right? And here we can prove that so the reachability set is the set of measures for which, such that for any random variable, which is FT adapted, whose conditional law is equal to mu, we can find the control for which this holds. And given this formulation, we can prove the dynamic programming principle. And you see here, because we are conditioning on the Brouwer motion, so this holds for all stopping times that are stopping times with respect to the filtration generated by the Brouwer motion. And this is useful because once you can simulate the Brownian motion, you can always define this holding times, right? Okay. The proof of this is based on what I mentioned before, so the selection theorem and the fact that in a adaptive process, a progressively measurable process can be written as a function of omega 0 and omega 1, right? So how about dynamic programming? So we follow exactly the same scheme here. We want to prove that the indicator function of the complement of the reachability set solves a Hamilton-Jacobi-Bellman equation. More precisely, Sonner and Touzy and their teams prove that V is a discontinuous viscosity solution of a fully non-linear second-order partial differential equation. Very long to read, right? So you see here that this function is a function of a measure, right? And if you think of the concrete situation, you would immediately realize that this is a very natural way to look at the problem, right? So what we do here, you would exactly, because we are dealing with a Hamilton-Jacobi-Bellman equation, so we need to lift and to differentiate, devise a linear partial integration by part formula, the integration by part formula, or an Ito formula, and so forth. So this is done. Everybody knows about this. You are very well familiar with this lifting idea. So we transpose the problem from a problem on a space of probability measures to an L2 space, which is Hilbert space, which means that our AGB equation is a Hilbert space valued AGB equation. That means I get back to the infinite dimensional case that I tried to avoid in the beginning, right? So this is the standard way to differentiate by now, a standard way to differentiate on P2. I will not repeat it. So this is the chain rule. And this chain rule is very interesting because it highlights the fact that we are quenching the diffusion. So we are conditioning with respect to the Brownian motion, right? And the way to prove this is just to get back to the particle system, apply Marquin's technique or propagation of chaos technique, and start with the empirical measures. Verify this because when you apply this for the empirical measures, you get finite dimensional E2 formula. You apply for it, and you let n go to infinity, assuming doing a lot of assumptions. A very good reference of these techniques is in the book by Vasily Kolokoltsov. He has a nice book on this kind of techniques. So here, because we are quenching, so we get the coefficients are conditioned expectations with respect to Brownian motion. All right. Of course, once we have this, we may use the lifting or we may use unifunctional. We get exactly the same thing here. So you know exactly if in order to derive a Hamilton-Jacobi-Bellman equation, you just start with the E2 formula and take the expectation, identify sub-martingale, and then the optimality is reached by martingale, right? And then you get your AGB equation. This is exactly what happens here. So the PDE is quenched, so it is of this type. So you recognize. So this is the generator. So this is exactly the generator, and this is the Hamiltonian. What is specific for this kind of problems is that the Hamiltonian, the supremum is taken over the kernel of the matrix A here, the diffusion matrix. This is a well-known result in theory of flows in differential geometry and geometric geometric control, right? So this is so our Hamilton-Jacobi-Bellman equation looks like this, but the calligraphic H is just a conditional expectation. So for us, this is something new. I have never seen this in the literature, and it is very natural because if you if you see B as a common noise, this is exactly the effect you want to see on everything related to this system, right? So you may ask whether this equation has solution or not. Is there any uniqueness result? Is there any comparison result? So how about, so there is no, how about the terminal conditions and so forth? Of course, people like Bouchard and Karoubi are very clever, so they figured out how to do it, right? So this is the continuity assumption. This continuity assumption is somehow odd. We cannot avoid it. It just says that we need, because we are dealing with Hamilton-Jacobi-Bellman equations, so we are looking all the time for feedback type controls. So this is one instance of this idea. So we would like to ensure existence of a regular feedback control close to the kernel or N0. So this is, of course, highly technical. So we assume it, and given some conditions, we could prove that there is a viscosity super solution to this equation, but under the continuity assumption, this solution is also a subsolution. There is a subsolution. We don't have a uniqueness result here. And for the terminal conditions, we take the lower and upper semi-continuous envelopes. You may ask, what is this? Or is it useful in practice? Yes, it is useful in practice, because usually when you deal with crowds or when you frac, you don't look at a particular molecule of water that you pour in the well. You look at a kind of shape. And looking at the shape makes this idea of upper and lower semi-continuity or the envelopes very natural. So what we see here, so we are moving clouds of particles from one point to another point, from one place to another place through a diffusion process. Okay, so this is exactly what we have achieved. So we found a seemingly new stochastic target problem. I don't know if there are some potential financial applications, but engineering applications are many, right? And the goal here is to try to perform some simulations to solve this cracking problem. They have a huge amount of data. I don't know if you have been in contact with this oil industry. So they have satellites, so they have online data on the pressure, the volumes, the type of the geology of the wells and so forth. And these are reported on a daily basis, basically on minute by minute. So they have all this, they track them by satellite, and they can see them online, all right? So given this information, we would like to try to simulate this kind of problems, right? Of course, we should start with a simple problem, a linear problem, and see what happens, okay? So the technical question that we don't know about is uniqueness. We don't know how to solve the problem for the unconditional law, simply because when we use the conditional law with respect to Brownian motion, then we use the whole structure of the Brownian motion and the structure of the Lebesgue measure on 0, 1, right, to create these flows and these nice feedback properties. So the hope is to use numerics for quenched PDEs. And of course, Brownian motion is only one noise. In practice, you have like the social force. The social force is a constant noise, right? So it is there. It doesn't fluctuate, right? So we would like to look for other type of process, like jump processes, or processes with long memory, which is something that geologists observe in this kind of technology. So these are some references. So the reference number 2 and 5 and 6 are those related to this physical interpretation of movement in random media, the importance of quenching and annealing. And they are used by physicists to create big simulation machines to model stars and so forth. Probably this would be useful even in our small application. Thank you very much.